VLSos here. This is a video lesson on types of limits. This is a quick review of the types of limits that there are and the terms that we use to refer to them. I'm going to sketch a graph to help us. Let's call this the g function. And for some reference points, let's label a tick mark at 1 and 2 on the horizontal axis. Let's make this 2 on the vertical axis. We can use limit notation. In this case, we're going to talk about the limit as x approaches 2 from the right on g. And that limit will have a value if it exists. Notice that the notation lim4 is short for limit, and below it we have our approach statement. The horizontal variable is approaching 2 with a plus superscripted to mean from the right. And then we refer to the curve, we're talking about the function g. So we are approaching 2 in the domain. We could imagine that we are coming from the right, but our motion is left if we're approaching 2 from the right. And we think as we come from the right that we will get to a value, maybe of 4. In this case, then, where we think we're going to be is the answer to our limit. But there is no function value at 2. The function is undefined at 2. So we can't say that the value of f of g at 2 is 4, just the limit, from the right side in this case. We can change the limit notation just slightly to approach 2 from the other direction. In this case, the minus means from the left of this same function. When we do, we could imagine that we are on the function traveling right because we're coming from the left. Where do we think that we will end up? Again, at 4, even though we don't have a value of the function at 2. We could say, as a reminder, the g function evaluated at 2 does not exist. We'd also say 2 is not in the domain of g. Because these one-sided limits are equal, then we could ask the absolute limit, or the limit as x approaches 2 without being modified by a plus or a minus, implies that it's the absolute limit of g, and because the two one-sided limits are equal, it does exist and is also equal to the one-sided limits. All of these limits are called finite limits. Finite is not infinite. These two are one-sided because you're only concerned with approach to that location from one side. This one is called absolute. And when you ask a finite limit question and you don't specify whether it's coming from the right or left, it's implied that it's an absolute limit. So if I was to vocalize the question, what is the limit at g, it's implied that I'm asking what is the absolute limit at g. There are finite limits, and these are their types. We also have infinite limits. These infinite limits tell us about the end behavior of a function, what's happening on the two ends of the function, implying that the function is going to be represented or go in both directions, positive x and negative x. So we could ask, what is the limit as x goes to infinity of the function? And from the graph, which is all we have to go on, it appears that this arrow is suggesting that g is going to continue to increase to infinity. So the answer to this question is infinity. There's another end, the left end, and the notation for it is the limit as x approaches negative infinity of the function. And if we look at the graph, the nature of this curve seems to be suggesting that it doesn't go down to a negative infinity. It does continually go down, but it never crosses or reaches the value of 2, or represented by the horizontal line at y equals 2, which suggests that the limit as x goes to negative infinity is approaching that asymptote, so its limit is 2. These limits are infinite limits because their approach statement involves infinity. We could ask, well, we could write the notation, what is the value of g at negative infinity? But similarly, the notation g of 2 doesn't exist. Asking this question in function notation is ill-formed because we can't put negative infinity into g. Negative infinity is not a value, so we can't ask what the function is at that value. Limits are required in order to understand the mathematics of infinity. This here is inconceivable. We do not have a concept of infinity as a value to be used as the input to a function. So sometimes we say this is an ill-formed expression or use of notation because it's inconceivable.